Today we're going to start working on three-dimensional geometry. So this is a gigantic field of research, field of study that we're going to only cover a little bit of. Our main focuses are on surface area and volume, which you should already be somewhat familiar with. And we're also going to talk about spherical geometry and a little bit of non-2D geometry stuff. But there's lots and lots of stuff that we're not going to talk about. So if it's something that interests you, then you can research it and learn way more about it than anything we're going to do in this class. So starting out, we're going to talk about some vocabulary. So our first thing we're going to look at is a term called a polyhedron. This probably looks kind of familiar as an analog to polygon. So poly, same thing, means many, and whereas gon was talking about many sides or many angles within 2 dimensions. So this is a 2D figure made of line segments. This one is a 3D figure, which we call a solid, made of polygons. So basically it's the next dimension up. Instead of a 2D shape with all straight sides, it's a 3D shape with all flat faces. So a polyhedron, there's like infinitely many polyhedra, but they don't include anything round. Just like polygons exclude circles and anything rounded like semicircles or ellipses, a polyhedron doesn't include cylinders or spheres or cones or anything with rounded faces. So next thing we have is a face. So a face is a two-dimensional, let's say a planar, side enclosing space. So if you think about like a cube or a rectangular prism, it has 6 faces. It has a top and bottom, a front and a back, and a left and a right. So each of those are faces. Faces can be polygons or not. So you can have, we have what we call bases, which are like top and bottom sides, and then we have lateral faces, which are the ones around the side. So, for example, on a cylinder, you have, I guess you wouldn't call this lateral surface area a face, but it is part of its surface. So I think we could say, no, a face can definitely be a circle because this is a face. So these bases are faces of the cylinder. So it doesn't have to be a polygon, but it does need to be planar. So these are faces, but this is not. These are all faces on this one. So whether they are faces or not, a shape is, when you completely enclose it, we call everything around the outside of it its surface. So this is basically all area enclosing space, a space. So a surface is like all the faces added together, and it could be, we talk about lateral surface area, which is like the part around the sides, and then bases, which are like top and bottom. Next thing would be an edge. So edges are where faces meet. And they are, so we have different kinds of edges. We have a circular edge here at the top of this cylinder. We have a linear edge here at the left side of this cube. But basically anywhere 2 faces meet, we end up with edges. Vertex, just like in 2D, so this would be where 2 faces meet because we know that planar things intersect in a line. Vertex in 3D is where 3 or more faces meet. because we know that 3 planes can meet at a point, but more than 3 can also meet at a point. So we'll see examples with 3 or more faces meeting at a vertex, but it's basically a corner, whereas an edge is like a line or a line segment. Convex has the same kind of meaning it did for polygons. So convex means that all the vertices are pointing outward. And a way to define that is that any point you connect on the surface will always be internal to the solid. So any segment connecting 2 points on the surface lies within the solid. So basically, if I pick any 2 points on this cylinder and connect them, the segment connecting them is inside of the cylinder. It never goes outside of it. A concave solid would be one where there was an external connection between the things. And then regular is the same idea as with regular polygons, is that something is repeating over and over. So in polygons, we had a side length, and if we made all segments be that same side length, it was regular. And we saw that the more sides we added, the closer we got to a circle. So I can add more and more sides, and the shape gets closer and closer to being a circle the more that we add. So a regular polyhedra, or regular solid, is going to be made up of, so let's say all faces are congruent regular polygons. And at every vertex where they meet, you have the exact same number of them meeting. So let's look at a picture of what regular polyhedra look like. So unlike 2D polygons where we could add infinitely many sides and just get closer and closer to being a circle with little teeny straight bits around it, there's only 5 ways to create a regular polygon, a regular polyhedra. So regular polyhedra are these 5. They are called the Platonic solids because Plato was the one who, I guess, most famously described them. And they are made up of either triangles, squares, or pentagons. The reason is, if you think about taking a point and making that one of the vertices, we said that all polygons that meet at that vertex need to be congruent. So if I made 3, and we have to have at least 3 polygons meeting at a vertex in order to create a solid. So if I created these 3 triangles and then basically treated this like a net and folded them up so that this side connects to this one, I would end up with this first shape. If I added another triangle to that and then folded it up so that this side connected to that one, I would end up with the top half of this middle one. So I have 1, 2, 3, 4 equilateral triangles, and then on bottom, there's kind of a mirror image of 4. So at every vertex, there's 4 equilateral triangles meeting. And then finally, if I make a 5th triangle and connect here, then I end up with basically the top part of this last shape. There's 5 triangles around that, and at every single vertex, you can see 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5. So every vertex has 5 equilateral triangles that meet at that point. The squares, so to finish that off, if we added one more triangle, then we couldn't fold the shape up anymore. It would be flat, and it would just become a regular hexagon. So it wouldn't work to make a 3D shape out of that. On the squares, I can take, if this is my vertex here in the middle, I can make 3 squares and then fold it up so that this one meets that one, and I end up with this cube shape. But if I add a 4th square, then again, I've created a planar polygon, and I can't fold it anymore because it's flat. So there's no way to add more squares. And then with pentagons, if I have this point, I can make 3 pentagons around a point. So say like 1, 2, 3. These are going to look probably pretty bad. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Something like that, to where then I can fold this together with that one, and we end up with 3 pentagons that meet at every vertex on this shape. But again, I don't have room to add another pentagon. If we go up one more shape to hexagons, and I try to put 3 hexagons together, then they are going to, so let's say our vertex is over here. So I have this hexagon, 1, 2, 3, 4. Those need to be straight. 1, 2, 3, 4, 5, 6. And then, let me actually just use real hexagons, because I cannot draw hexagons well enough. So hexagon, if I have 3 of these meeting at a point, then I end up with a complete circle. So just like with the other shapes, once I reach a full 360 degrees at the middle, then I can't fold it anymore. So with hexagons, there's no way to fold the shape together to create a 3D shape. And that will be true for anything bigger, because remember, we need 3 polygons to meet at each vertex in order to create a 3D shape. So nothing bigger than a pentagon can create a regular solid. So we just have these 5. They're the only ones in 3 dimensions that create regular polyhedra. They have names based on their number of sides, just like we named polygons like pentagon, hexagon. We name these based on their number of faces. So this first one has 4 faces. So the prefix we use for 4 is tetra, so we call this a tetrahedron. The second one has 6 faces, and yes, you may also call this a triangular pyramid or a equilateral triangular pyramid, but its technical name is a regular tetrahedron. So any 4-faced polyhedron would be a tetrahedron, and this is a regular one. The cube is our regular hexahedron. So just like a hexagon has 6 faces, a hexahedron has 6. Hexagon has 6 sides. Hexahedron has 6 faces. This one with 8 faces is called an octahedron because it has 8 faces. This next one has a total of 12 faces. So it has 1, 2, 3, 4, 5, 6, and then 6 around on the back. So this 12-faced shape, just like a 12-sided polygon is a dodecagon, we call this one a dodecahedron. And then finally, this last shape has 20 equilateral triangle faces, this red one, and we call it an icosahedron. And these are also typical dice used in tabletop role-playing games like you saw on the warm-up slide. So these are called a D4, D6, D8, D12, and D20 within gaming, using them as dice. But on the warm-up, you may also notice that there are 2 that don't fit that. So we have our 4-sided, our 6-sided, our 8-sided, 12, and 20. But then we have these 2 guys that have 10 sides. So we count in a base 10 numbering system, and 10 is a really important number for us. So we kind of create these dice that are not regular polyhedra. They don't fit the pattern of the other ones, and their faces are actually made of kites rather than regular polygons. So we're so ingrained in base 10 that we need a 10-sided die just to make sense of our world, basically. So there are a lot of other solids that are semi-regular. Archimedean solids are some of them. There's other ones besides that. So basically a semi-regular is at each vertex you have the same set of polygons meeting, but they don't have to be all the same polygon. So I could connect triangles and squares or hexagons and squares. As long as every vertex has the same shapes meeting there, it's semi-regular. So those we don't have, I mean, there are names for all of those. We're not going to go into the names. So that's one of those things that if you want to learn more about, there's way more you could learn about it. So within any polyhedron, we have this formula called Euler's formula. It applies to all polyhedra. And it relates the number of vertices, edges, and faces that any polyhedron must have in order to be an enclosed shape. So we said that edges are all where two planes meet, and vertices are where three or more planes meet. So the way it works out is, and there will be a video on Canvas going kind of more into the details of why, but the way it works out is that we can take the number of vertices and we can subtract the number of edges, add the number of faces, and that's always equal to 2. So let's look at that just in the context of a couple of these regular ones, but it applies to every polyhedron, whether it's regular, semi-regular, or not. So we have our vertices. So we had 4 faces here. Vertices, we have 1, 2, 3, 4. And edges, we have 1, 2, 3, 4, 5, 6 edges. So the formula says F minus E plus V equals 2. I think I had the V and F the other way on the other slide. It doesn't matter as long as we have the edges are the one that is subtracting from the other two. The order really isn't important. Sometimes it's even written as F plus V equals E plus 2, so it doesn't really matter. So here we have 4 faces minus 6 edges plus 4 vertices is equal to 2. So if we were missing one of these quantities, we could solve for it based on knowing the other 2. So if I told you I have a polyhedron with 20 vertices and 18 faces, then you would be able to calculate that, although I think that's impossible, the one I just made up. Let's look at the cube. On the cube, or the hexahedron, we have 6 faces. We have 1, 2, 3, 4 vertices at the top and 4 at the bottom. So we have 8 vertices. And we have edges, 4 on top, 4 on bottom, and then 4 around the side. So we have a total of 12 edges. So if we use our formula, it says 6 minus 12 plus 8 should be equal to 2. And that's 14 minus 12, so that checks out. So that's just a formula that you can use to figure out how many vertices, edges, or faces a polyhedron has if you know the other 2. All right, the last thing I want to talk about today is the idea of turning 2-dimensional geometry into 3-dimensional geometry. We kind of talked about nets a little bit already. So nets are basically an unfolded shape. So if you take all of the faces and fold them out flat, then you get a net. And you could think of it as being like a box that encloses the volume of the solid inside of it, but is actually hollow. This is a way you've probably seen 3D figures before and seen them as like unfolded net shapes. But there's other ways to go from 2D to 3D that are not just folding. These are really good for like regular patterns and seeing kind of the shapes, the polygons that create them. But coming from an engineering background, we create solid geometry in computer programs using things called cross-sections. So this is a picture showing a concept called extrusion. Extrusion is taking a 2-dimensional shape and extruding it or pulling it into 3 dimensions. So if I drew this trapezoid right here, then I can extrude it into 3D by basically pushing it or pulling it in that dimension that's perpendicular to my shape that I've drawn. So what I end up with here is some gold bar looking kind of shape, and I can extrude it however far in this direction. But the idea is wherever I cut through it, like here, this cross-hatched part is called a cross-section, and that's always going to be the same as my original sketch was. So this original sketch up here is the same as the cross-section anywhere I slice a plane through this, as long as the plane is parallel to or perpendicular to the extrusion direction. Now, I could slice a plane through here going a different way. Like I could make a plane going this way through the shape, and it would have a different kind of cross-section. So if I did that, I would end up with a long rectangular cross-section going that way if I was looking, basically sliced through top to bottom and looked at it front to back, or from this side. So depending on where you slice through a three-dimensional shape, you get different cross-sections. And the constant cross-section is only if you are perpendicular to that extrusion direction. I also included this little Play-Doh toy. You may have seen something like it where you can push the Play-Doh through one of these little windows and you get a shape that is basically the same idea as this. It's an extruder that uses this cross-section to create a long piece that's all has that same cross-section all the way through it. Another thing we can do with sketches, besides just extruding them out in a straight direction, is called revolving them. So here I've drawn a triangle and extruded the triangle around this long axis to create a tall cone. So basically think of this triangle is spinning around this axis, and anywhere I cut through, I'm getting that same triangle right here. So the cross section, this is like a quarter section, but if I cut through the entire plane, I would end up with a triangle that was like double this one. So if I sliced a plane through like vertically like this, then I would have this triangle, and then this front part would be taken away, and I would have the second triangle right here. So revolving depends a lot on what axis you revolve the shape around. So I've drawn the same triangle 3 times here. In the first image, it's revolved around its tall axis or long axis, and I get a tall cone. In the second one, I've revolved it around the shorter side of the triangle. So that's spinning the triangle around this way, and I end up with a short, wide cone instead of a tall, narrow one. And again, you can see that the triangle here, this is the axis that it revolved around in the middle. Then in the last one, I've revolved it around an offset axis. So an axis that's away from the triangle so that there is space in here in between the triangle and the axis. And that space here ends up being a hole in the finished shape. So just showing the idea that depending on what you revolve the shape around, you can actually end up with very different results for your three-dimensional shape. And then I want to go back real quick to here just to talk about some of our basic shapes that we're going to be looking at. Prisms, I think you guys know, are 2 bases that have lateral faces connecting them that are all congruent or all rectangular. So basically has a flat top and bottom and then rectangles connecting it. Cylinder is like a prism but with a round top and bottom, or circular top and bottom, and then a lateral surface connecting it. Pyramid is basically like a prism, but instead of 2 polygon bases, it has 1 polygon base. And then a top point we call an apex. Everything connects to that apex rather than connecting to a congruent base. Cone is like the same thing for a cylinder. It has a point that's an apex, and the cone connects up to that. And then spheres are like a ball, like a round shape that is kind of like, if you think about revolving, like you took a semicircle and spin it around this axis in 3D to create a 3-dimensional shape. You may have seen like paper folding things that unfold and have a bunch of like paper semicircles, and you fold it around to connect to itself, and it makes a sphere. So that's our intro to 3D stuff. Just an brief overview. We'll go into surface area and volume of all of these shapes in the next couple of days.